Hello guys, welcome back to my channel. As on African motives, still working on engineering science N3. So in this platform, actually we have got the question paper which was written in July 2021, which is an X paper. So as you can see guys, that's what we have for engineering science N3. So we shall have to work everything that we have here guys are the instructions. Remember your instructions and everything. These are things which are very, very important whenever you are answering your questions. All right, these are the things that are very, very, very important in your answering of the questions. So that's what we have guys. And quickly rushing through the questions that we have here, we have got the first question, which is actually on motion, power and energy, where we are given the first question there just to define the term speed. So guys, as we know that speed, that's the rate of change when you are talking of what, of distance, which is actually measured in meters per second. So don't forget that speed is measured in meters per second, and some of you can write this as meters per second like that. It's still one and the same thing. All right, but that is what we have as a definition for speed. And to state the law of conservation of energy. So I think I have talked about this a lot of times, that whenever you're talking of energy, you can't do anything to have it, to destroy or to create it, but what you can do is that it can be converted from one form to another. So that is all about energy, that it cannot be created or destroyed, but can be converted from one form to another. So only that is what you can actually do for energy there. All right, so anyways, that's what we have. Then we are given that there is a body of mass of 5 kgs, which is accelerated from 6 meters per second. So okay, in this case it's already in meters per second to 15 meters per second. So let us just take our information here and also take note, it's up an incline in this case. So this body is going up an incline. So let's just take our information for this particular body that we have. So we're given a body which is up an incline like that, and we are given that this body is having a mass of 5 kgs. So this is the mass that we are given. So we are given a mass of 5 kgs, and it's already in kgs, so we don't need to convert. And it accelerated from, all right, we are not given the acceleration, but we are given where it started to accelerate, that is the velocity. That is what we are given. So we are given the velocity of 6 meters per second to 15, which means its final velocity. So you've got u, which is the initial 6 meters per second, v, which is the final, which is 15 meters per second. That one, it's 15 meters per second during a period of, we are given 20 seconds. So what is that in seconds? That is your time. So we are given the time in seconds of 20 seconds, up an incline making an angle of 25 degrees to the horizontal. So you're given an incline which is making an angle of 25 to the horizontal. So this is our incline to the horizontal. That is an angle of 25 degrees, which is our theta. Then the frictional force is 45 newtons. So you're given the force due to friction. So that is what we are having in this case, the frictional force, which is actually 45 newton. All right, so this is what you're having, is this body is going up an incline like this. Then it means there is a force that is going to oppose that, which is the frictional force. As we know that it opposes to the movement that will be taking place. So anyways, in this case, we are given to calculate the acceleration of the car, of the body that is being accelerated. So in order for us to have the acceleration, in this case, we can actually work with, so going back to our linear motion guys, we have got the initial velocity, the final, and also the time. So we can actually play around this information. Remember from our formula sheet, we've got the formula V is equal to U plus AT. So and we've got v, we've got u, we've got t. All that we need is the acceleration, so we just need to make that the subject, or you can just substitute your values here, or we can simply make a to be the subject by transposing v to this side. U to this side is going to be minus u, then divide by t, so that you can find your acceleration, which is going to be v minus u everything over t. So it's just a matter of substituting, guys. As we can see, we've got our v, which is 15, our u, which is 6, so this will be 15 minus 6 over the given time, and the time that we took is 20 seconds. So that is what you just have in this case. So simplifying this properly from our calculator, we are going to obtain 0.45, which is in meters per square second. All right, so you can write even this as meters per square second like that. It's still one and the same thing, or you can write it like this. This is our acceleration. All right, so I shall just keep this aside. Maybe we might need to use this, I don't know. So let's move on to another part on the other question, where we are now given to calculate or to determine the distance that was traveled, and there is 3 marks for that, the distance that was traveled. So the distance is actually the length of gradient. Okay, now we've got our acceleration here. Let me just write it. We obtained 0.45, remember. All right, so the distance we're actually referring to the straight that is from this point. Let's just say this is our A and this is our B. So we are just saying at A, that is where we have 6, and at B that we have got 15 meters per second. So what is our S in this case? So we can actually use again the information that we have, the time, the initial velocity, the final velocity, and also the acceleration. So we can use any, so there are so many formulas that you can actually use in this case. So I'm just going to take this one. Remember that 2as is equivalent to v squared minus u squared, and also s is equivalent to ut plus half at squared. So which means you can use this formula. It must give you the same answer with someone who used this formula. Since I want to calculate s, I'm just going to divide by 2a both sides, so that I can remain with s. So that means s is equal to v squared minus u squared over 2a, where I have got my v and my u. So it's going to be 15 squared minus 6 squared. So it's 15 squared minus 6 squared over 2 times a, which is 2 times the acceleration. Take note, the acceleration, you have got it, you determine this, you got 0.45. So that's it, guys. Or we can just substitute here ut, that is your u, which is 6, your t is 20 here, so it's 6 times 20 like this, plus half at squared. So it's going to be half of a, which is the acceleration, 0.45 times t squared, which is our time, which is 20 squared. So you must obtain the same answer, like I'm saying that these are the formulas from the same group, so they must give us the same answer there. So in this case, simplifying, we are going to obtain something like 210, provided that we simplify this properly. This will give us 210 meters. All right, so that's what we had. Let's see another question, which is on 1.33, which is the work done by the component of gravity force parallel to the plane. Take note, this is the work done by the component of gravitational force. So what are we talking about here? If you are talking about the work done that was done by the component of the gravitational force, and it's a parallel to the plane, which means definitely we are working with this case here. Let me just take you back. We know that actually here the work done is going to be force times what? Times the distance. So what we need is to find that which is force times the distance, which is our Fs, so that we can actually determine the resultant. All right, means definitely we have to work with the parallel component in this case. So this is 1.33, where we have got the work done, which is the force times distance. But which force are we working with now? They said parallel to the plane, the gravitational force. So we are going to work with the gravitational force, which is parallel to the plane, which is our F parallel, or we can have this as Fs. Remember, it's just one and the same thing here. So our work done is simply Fs times the distance. So whereby our Fs, we know that it's W sine theta, which is equivalent to mg sine theta. All right, so that's what we are going to have. So this is our force due to what? Due to gravity for the parallel component. So we need this. Okay, so that is let's substitute our information, guys. Where did I write this? Okay, I have it here. So that's our mass here, which is 5 times the gravitational acceleration. Remember, it's 9,8 times sine theta, which is the angle of inclination of 25 degrees. So this will be sine at 25 degrees, like that. All right, so if we are to simplify this properly, we are going to obtain 20,70829. So these 2 cannot change this 8, so it would remain like this to 3 decimal places because there was a 2 there. So now we have got our force here, which is due to the gravity for the parallel component. So now the force 20,708 multiplied by the distance that was traveled. Remember, we calculated our distance here. We obtained 210 meters. So which means we are going to multiply here by 210. So now we have got our work done, which is going to give us 4348,68. Yeah, that would be 68 there. So remember, this is work done, which is measured in what? Which is measured in joules. So that is the idea, guys. So if you are working with this, take note, what are you being given to calculate? All right, what are you given to calculate? And also the information that you have, how are you going to present that information is very, very important. Okay, another question is to calculate still on work done, but this one is by the frictional force. So still it's one and the same thing, just like what we did, guys. We said work done, it's force times distance, but this time they said by the frictional force. So which means we are talking of work done which is being affected by the frictional force times the distance. So just like that. And we have got this frictional force, we have it, which is 45 Newton. Remember, we were given in the beginning, we already given this, so it's 45 times already the distance. We calculated this, so that's 45 times 210, which is going to give us 9,450 joules. So that is our work done there due to the frictional force. Then let's see another question now. They are saying the power that is being exerted by the total force. The power. All right, remember, when you are working with the power, it's all about the energy that is being used over the time taken, and that energy, in this case, we are taking it as the work done. So we are going to have the total work done in this case over the total time which was taken. But now they are saying this is supposed to be due to the total force. Take note here, due to the total force. So what then is going to represent our total force? All right, this is what is going to represent our total force, guys. Our total force is going to be work done is going to be force times the distance. Remember, that's our work done, force times distance. So we are going to have the total force, which is F up. That is your total force, because remember that this part is going up the incline, and as it is going up the incline, there is a frictional force that is opposing that. There is a frictional force that is opposing that. So remember, your F up here is going to be, let me just write this, this is our F up like this. All right, we be having here our parallel component, all right, which is our, I'm focusing with the parallel component here. So as we can see, the frictional force and the parallel component here, they are going in the same direction, so which means the sum of these two are going to actually give us this F up. So our F up, which is going to be, and also this formula, you know that you are given for F up. Okay, so our F up in this case is given as the frictional force plus the parallel component, and we calculated this. We have got this, okay, 45 plus the parallel component. We calculated this and we obtained something, guys, there. And now these things, they are too many, but I have got this value here. So anyways, it was 20.708. Still remember this value. So if you add, this is gonna give you 65.708 in Newton. That's our F up. So now what can we do? What can we do with this value? Remember, we want the total work done, which is going to be used here. So we have to calculate this 65.708 multiplied by the distance. This is not going to change. It's still the same 210, this one that we obtained here. So multiply by that 210, and this is going to give us our work done now, which is 1379.8,68, and this is our work done, which is measured in what? In joules. So if this is our work done, therefore the power can be taken, because we've got the total work done. Actually, this is the total work done. So if this is the total work done, therefore we can actually have our power, because power is work done over the time, and we've got the time. Yes, the time is there. So we are going to simply divide 1378, no, not 78, but 798. This is 798.68. So that's what we have for the work done, which is over the total time. The time frame which was taken in order for us to go up the incline was 20 seconds. So that's it, guys. This is in joules, this is in seconds. So definitely if you divide, you're going to obtain 689.934. Yeah, that would be 934, something like that, which is in joules per second. But this is joules per second, which we know that is equivalent to a watt. So this will give us a watts. So that's our power in watts, because joule per second is equivalent to a watt. So you can write even in kilowatts, that one would be 0, something. So even to leave it like that, it's best. It is best for us to just leave this answer like this. Anyways, let's see what we have on the other part there, which is to define. Okay, define the term uniformly distributed load. Okay, so this is what I'm having. Also for this formula, the uniformly distributed load, which is given, it is a load that is spread evenly over the length of a beam, or over the part of a length of a beam. So whereby you'll be given a force of maybe 9 kilonewton per meter or 5 newton per meter. That one is a distributed load. It will be given over a certain length, or over the total beam that you're given. Then instead, the law of moments. So as we know, guys, about the law of moments, it's all about the clockwise moments, which are taking about a certain point being equal to the sum of also the moments that will be taken in another direction. So it's all about the direction, either clockwise or anti-clockwise. That is what is important, being taken from the same turning point, which is the same fulcrum. That one is very, very important for you to indicate whenever you are giving these definitions. The term fulcrum or the term turning point must be indicated properly. Okay, then we are given that there is a beam which is 6 meters long on 2.3 and is supported 1 meter from the left end. Okay, so I think the best that we can do is to just because here we are just given to calculate the action of the two supports, how without the diagram. So we just need the diagram. So in this case, let us just draw our diagram. As we are drawing our diagram, I'll be explaining a lot from that. So I think that is what is best for us to just do here. All right, so let's just draw our diagram. I have my ruler here. This is a beam that we are, let's just say, okay, let's just have it like this. All right, I'm just going to put it in a simple way so that we can understand what is happening in this case here. So there is a beam which is 6 meters long as we are given and is supported, take note, 1 meter from the left end and 2 meter from the right end of the beam. Okay, so we have got 1 meter and 2 meter. All right, here there is 1 meter. I don't know, maybe let me just increase this. Is it going to be clear? All right, anyways, I hope it's going to be clear. So it is supported 1 meter from the left. So this is our left end. So 1 meter, which means you're going this way. So there's something like this here that is 1 meter from the left end. So let's just say this is our left end, and we've got 1 meter in between here. Is it 1 meter or 2 meters, guys? This is 1 meter. All right, 1 meter. Then the other one is the one that is 2 meters from the right end. Okay, so this one is 1 meter. All right, so let's just leave it like that. Then we've got another one which is 2 meters from the right end. So let's just say we've got here our 2 meters, or we can even put it here so that it can be clear. All right, this is just a diagram, guys. You can draw something which is much nicer than I can do. So you can even draw something which is much nicer than I can do there. So we have covered which question? This is just 2.3. All right, we have covered 2 meters there. And also take note here, there is a uniformly 12,4243 kg per meter, that is kilogram per meter, placed in between the two supports. Okay, so which means we are given a distributed load in between these two supports. So there is a distributed load here in between these two supports, which is 12,243 kilograms per kg. So in between these supports here. All right, that is where we are having our distributed load here. This is our two supports like that. All right, so now if we are having this in between these two supports, guys, then we need to know, because this is actually mass per meter. You are given mass. Okay, so which means we need to find the force, which is the work done, which is the weight of the what, the weight of the given load that you are given, because this is a load that you are given, but it's a point load, it's distributed. So therefore, what is the force, or what is the weight of that? So remember, weight is equivalent to mg, which is our force. So we've got the mass of 12,43. So this is 12,243, guys. Why am I still repeating this for? So it's 243. So this is actually per meter. So you are going to multiply by 9,8 like that. Okay, and this is going to give us, if we multiply by 9,8, it's going to give us 120. So this is actually per meter, remember. So you're going to have 120 Newton per meter. So that's our force, or our work done, that we are having in this case of 120. So let me just put it in this way, sorry. sorry for that, guys. This is 120 Newton per meter. All right. So then, if we are to know, well, remember we are given that this beam that you are given here is 6 meters long. So definitely here we have used 2 meters, 1 meter. So 2 plus 1, that's 3. So which means in between here we are going to be left with 3 meters. So if it is in between 3 meters, that means we can just put it this way, just for our calculation reason, but the diagram is not supposed to be there. This is, we are just putting this for calculation reason so that we can know what's happening between this 120 Newton per meter. So remember, we are going to multiply 120 times 3 so that we can have the force. So 120 Newton per meter times 3 meters is going to give us 360 Newton. So now we can represent this with 100, or the 360, sorry, 360 Newton like this. But it is going to be now separated in between 3 meters. So 3 divided by 2, that's 1,5 meters here, and also 1,5 meters here. So this, I'm just putting it so that it can help us for calculations. It's not even important, as long you know that it's 120 Newton per meter and you understand how to use it. Therefore this is not important. But if you are like me, you want to actually understand what's happening here, you can just put this and it's going to help you whenever you're doing your calculations now. Okay, anyways, let's move on. There is another point load that is given, which is 300 Newton and is placed on both ends. So there is 300 on both ends. And which are the ends that we are talking about? The left end and the right end. So on the left end here is a point load facing downwards of 300 Newton. Take note, we are given that is 300 Newton, but it's on both, which means on the right end also there's a point load again of 300 Newton on the right end, like that. That is on both ends. All right, let's move on. And also, and a 200 Newton is placed, a 200 Newton load is placed 1 meter from the right end. Take note, 1 meter from the right end. This is our right end. And remember, we have got a support here which is 2 meters from the right end. But there is this one which is a point load which is 1 meter from the right end, like this. So in between here there's 1 meter. So we can even just put it on top, maybe, so that it cannot affect us. So there's 1 meter from the right end, which means also here there is 1 meter in, because in between it was 2 meters. So, and this one is given as a 200 Newton. All right, so we are given this as 200 Newton, like that. So that's our diagram, guys. I think everything is there, so we can just name our points so that they can help us while just calculating, to say that at this point this is our A, this is our B, this is our C, this is our D, and this is our E. Okay, so these are the points that I am going to work with. Now let's answer the question. The question is to calculate, or to have the reaction of the two supports. And which two supports are we talking about? According to our diagram, our supports is this one at B and this one at C. So these are our supports, this one at B and this one at C. So now, working with these supports, definitely I'm going to take my moments about B, then also about C. So taking moments about B, so this is 2.31 now, so I'm going to take moments about B, then I move on to C. Okay, so if I am working with moments about B, we are going to realize, we are going to see that according to B here, if we are to put it this way, this is our B and this is our C. C is moving this way, which is in an anti-clockwise direction. C going to B is moving in this direction, and this direction is what is anti-clockwise. So that means we shall refer to the sum of the anti-clockwise moments being equal to the sum of the clockwise moments, because we want to work with C on this side, so we refer according to C. But anyways guys, you can even write either way. It's not a matter of fact. Okay, so now what is the distance between C going back to B? There's a distance of 3 meters, so it's C times 3, which is 3 times C, or C times 3, whatever that you can write, which is going to give us 3C. Remember, it's force times what? Distance, which is moment. But the other thing, remember we are referring to B, and this is our B here. All right, we said C is moving in and anti-clockwise. We agree that. All right, now my question is, do we still have anything that is on the anti-clockwise? Okay, let's check. All these, they are moving clockwise. This is clockwise process. You can see this one is going to move this way, this one this way, this one, which is clockwise. But this 300 on the left side of B is going to move in this direction. Take note, it's a continuation of that direction. So which means we are still in the anti-clockwise, because this one is just a continuation like this from this point to this point. Take note guys, this is still a continuation of this R, so it's still anti-clockwise. So which means this 300 is part of the anti-clockwise moments, so it must be added together. All right, so this will be 300 by what? By 1. So we have to add also 300 times 1 in this case. All right, so that's it. So we are done with the anti-clockwise. Therefore we have to move to the ones which are moving in the clockwise, which is B to B. We've got this one clockwise. Remember, we said there's a distributed load, and we separated and said it's now 360 between 1,5. So it's going to be 360 times 1,5. So this one is going to be equal to 360 times 1. So you see that when you've got a diagram like that, it's going to be easier for you now to analyze what's happening. Then you move on to 200 back to B here. So this 200, remember, we've got 3 meters here plus 1 meter here. So it's 3 plus this 1 meter, which is 4 meters. So it's 200 times 4 meters. So that's 200 times 4. Plus we move on to the last one, 300 there at the end, which is 3 plus 1, which is 4, plus 1, which is 5. So it's 300 times 5. All right, so that's what you're going to have in this case. So combining these together, this is going to be 3C plus 300. Then definitely we have to combine what is on the right hand side, which is going to give us 2,840. If we do this properly, then transpose this, it's going to be a negative. So 3C is going to be 2,840 minus 300, which is going to give us something like 2,540. All right, so divide by 3 both sides, we can obtain our C. And this is going to give us 846,66, and this is going to be 666 and so on. So it's 667, and these are in newtons, Newton. So definitely this one will be in Newton. So this is our C. So it's according to our diagram. Maybe you used as left and right, I don't know how you wrote it, but this is our C, which is going to be 840. 6,667, which is in Newton. So that's it guys about the moments. So now we worked with the moments about B according to our diagram. What if we work on the other side, which means we can obtain another one? So we are going to take moments this time about C. All right, so taking moments about C. Now if we are to cross check B moving to C, it is going to move this direction. It is now B going to C, so it's this direction, which is clockwise. So this is actually clockwise. So we shall refer to the sum of the clockwise moments being equal to the sum of the anti-clockwise moments. So B to C is 3 meters, so it's B times 3, which is 3B. Okay, do we still have anything that is on the clockwise? Let's check guys. We are referring to what? To C, and we say this is the movement of clockwise. Remember guys, clockwise we are saying it moves like this. That is clockwise. So let's cross check this one, how it moves. It moves like this, which is also clockwise. Also this one is clockwise, but this force is now moving this direction, which is anti-clockwise, and also this one anti-clockwise. So these two moving to C, they are going in clockwise direction. So we have to add these two. We are adding this 200 and this 300. So it's 200 times back to C. How many meters do we have? 200 back to C. We have got 1 meter there. So it's 200 times 1. So we have to add these to the clockwise moments. Plus we move on to back to C. Here is 300. How many meters? There's 2 meters here. So it's 300 times 2, which is equivalent to the anti-clockwise now, which means take note that distributed load that we separated in between 1,5 and 1,5. So it's going to be 360 back to C. This was C here. So 360 back to C is 360 times 1,5. So it's going to be 360 times 1,5. All right, then we move on. Plus we have got this here, 300 back to C here. We've got 3 meters plus 1 meter, which is 4 meters. So it's 300 times 4. All right, so that's what we have, guys. So as we can see, all we need is to combine everything here. So this is going to give us 800 if we combine properly, which is going to give us, we add here, which is going to give us 1740. So definitely I have to subtract this on the other side of the equation, and we are going to obtain 940. In this case, 1740 minus 800 from your calculator, divide by 3 by 3. So that's our B, which is going to give us something like 318,3333333 and so on. So just 3 decimal place. It's going to be 333. So this is our B, which is 313,333 Newton, like that. All right, anyways, that's what we had, guys, for this question, which was to calculate the reactions of the supports. So you need to know your supports and so forth. So that's what we had. So on the other part is to draw a shear force diagram showing all main values. Where do we have the major values, or the main values in this case? So the main values that we are working with is here at A, at B, at C, at D, and at E. So this is what we need. And also the part of the distributed load here, we just maybe call it X. Is that X there, which is going to be showing, we shall see that part on the diagram. Anyways, let's see what we have. All right, this is 2.32. All right, so, and also remember, guys, when you are working with a shear force diagram, you are supposed to do a diagram in a proper manner, or in a proper presentation in that case. So this is what is going to happen, guys. We are not going to waste much time. I'm just going to take these ones direct. Remember, this is what is happening. At A, we are starting at 0 here at A, but there's a point load at the same point at A. So definitely it's going to be 0 minus 300. We are going to subtract that, which is going to give us minus 300, because we are having a point load. So this is going to be going downwards. So we started at 0 Newton here, but because of a point load, we are going vertically down. Draw a straight line vertically down up to a certain point, maybe this point. That's where we have got our minus 300. So this will be minus 300 Newton. All right, then remember, guys, what I told you about the shear force diagram, that you work with what you are given. Here there's a distance, there's nothing, there's no distributed load, so you just move a horizontal line up to B. So this one, you just move straight up to B, which means we are still on minus 300. Now at B there is a support, and every support it's a positive. So you are at minus 300, then at B there's a support, so which means you have to add at minus 300, you add 313,333 because it's a support, it is going upwards. So if you add this, you are going to obtain 13,333 Newton. So this one is going up because it's a support, this one. So it is going up to 13,333. Let's say somewhere here. All right, so that's where we have our 13,333 Newton there. So here I'm just giving you what you are supposed to do. All right, what you're supposed to do is what I'm giving you here. Then in between B and C, that is where we have our distributed load here. So which means we are going downwards 360. Remember, 120 Newton per meter times 3 gave us 360. So we are going to subtract 360 at this value that we are now. Remember, we are at 13,33333. This one. So at 13,333, you subtract 60 there, 360. So if you subtract 360, you are going to obtain minus 346,667 Newton. And this is a distributed load. Remember, it's supposed to be slanting like that. So this one is going to minus 346, which is definitely under this value because this is minus 300. So let's assume maybe it's somewhere here. So this one is just going, let me just put it this way, but you are supposed to use your ruler, guys. Okay, let's maybe somewhere here because it's supposed to be below, like this line. At this point, this is where we have our minus 346,667 Newton. All right, that's our distributed load. We are now at C. All right, direct at C, there is a what? There is a support, and I told you that a support is a positive, and it is a vertical line when you represent. So definitely we have to add the value of the support, which is at C here, which is 846, to this value here at minus 346. You add this value minus this plus this value, you are going to obtain 500 Newton. So this is going upwards up to 500, and 500 is above this value here. Take note, this is 13, so 500 is above, and we said it's a support. So a support is supposed to be a vertical line above. So this is what you're going to have. We are now at 500. Remember, when we added 846 to this value here, it gave us 500. So we are now at 500 Newton at this point, which is after C. So now for us to move from C to D, there's a distance between 1 meter, and there's nothing that is distributed here. So you just move a horizontal line 1 meter, okay, which means you are still at 500 here. You are still at the same 500. But what is going to happen? There's a point load which is 200 Newton, and every point load is a negative. So at 500, you subtract 200, which means you are going to be left at what? At 300 Newton, and it's a point load, which means you just draw a vertical line going downwards. All right, so you just draw a vertical line going downwards. At this point, you are now at what? At 300 Newton. All right, so this is our 300 Newton here. Then there's a certain distance of 1 meter again for us to reach the final point load here. So you have to maintain a horizontal line. So we are going to maintain a horizontal line which is 1 meter. Then we are at 300, but remember we are at 300 also here. So 300, where we are at minus the force of 300 there, is going to give us 0 Newton. So definitely it is going up to this point. Remember, here we started at 0, and this is at 0 here. So this must end at 0 Newton. This is a horizontal, a vertical line at 0, because this was still at 300. So 300 minus 300, that is a 0 there. So that is how you actually indicate. So that's it, guys, for the shear force diagram that we had. And now they are saying, from this shear force diagram that we have, can we determine the value of the maximum shear force from the diagram, what will be the maximum. So it's actually like we are just taking from to say, according to the values here, what is the maximum and like the value that can be reached. So the value that can be reached at maximum is where it actually crosses the horizontal line in this case. So where it is crossing the horizontal line at this point and at this point. So that's where we are having this here and also this here before it went. So we're having this here where there was a distributed load. So which means we have got a 13,33 and 346,667. All right, so that's what you're going to have in that case. So let's see another part of the question in this case, which is question 3, which is on forces actually, where we are given to give the similarities between the resultant and the equivalent force. The similarities, which means there is something that is common or something that we know about them. So we have the issue of magnitude and also that they're measured in newtons there. So that is what we have about the equilibrium and the resultant force. So draw a diagram indicating a tie and a strut on a single roof truss. So a tie and a strut, guys, I think this diagram is a little bit common to us. Remember what you'll be having if you are working with a roof truss, where you have got your supports here. So these are our supports, let's just A and B, and definitely you've got the forces, like you'll be pulling like each other, like pull like this, and this will be having compression, okay, pushing against. So this is a tie and this is a strut. All right, so that's what you just need there. So I think these guys, especially those who are doing those building science here, they know most about this a lot. They work with this a lot. Okay, the three forces in fig 1 are in equilibrium and on the same plane. So these are in equilibrium. So as you can see the diagram, everything is clear. There is nothing that we can change. All the forces, they are taken from the point. This one, everything is pretty nice. And also the angles, this is 50 degrees from the horizontal line, this one. So everything is pretty clear there. Determine the sum of the horizontal components. So in this case, guys, it's just to take everything is pretty clear. Horizontal component, remember you take with cos. So this is on the positive and this is on the negative. So this one is going to be 400 cos 40 on the positive. So it's 400 cos 40 degrees. Okay, we've got 200 is still on the positive, so you add that one. 200 cos the angle which is in between, which is 50 degrees. All right, then this is on the negative and it's a straight horizontal, so you just subtract that minus 650. This one is a straight horizontal force that we are given. So if we are to simplify these guys, we are going to obtain minus 215 0247. So it's going to change to 5 because it's 247 and so forth. So it will change to 5, which is measured in newtons. And also, if a horizontal is a negative horizontal, is this is either you are going to the west or you are going to the east. So this is a negative, which means this is going to the west. All right, so we are done with the horizontal. Move on to 3.2, which is to calculate the vertical components. Okay, so the vertical components, that's gonna be sine theta this time. So this is a vertical component and it's above the horizontal line. Whenever it's above, it's a positive. Anything below, it's a negative. So this one is going to be 400 sine. Remember it uses sine theta, this one, so it's 400 sine 40, which is a positive, and it's above the what, the horizontal line. So that's why it's a positive. If it is below, like this one, q, it's below, so it's going to be minus 200 sine 50. So it's minus 200 sine 50 degrees. And this one cannot be a vertical, it's a straight horizontal line. It can never be a horizontal, so there's nothing that we can take there. If you are to take it, then you have to use an angle of 180 there, which is going to give us a 0 definitely. So that's what we have, guys. And if we are to simplify this, we are going to obtain 103,9061. So this is 061553. So it's just going to remain like this. And vertical, it's either you're going up or down, and up it's north, down it's south. So this one is a positive, which means you're going to the north. So that's what we have. And in this case, the question on 3.33 is to calculate the resultant force that will keep the system in equilibrium. So here it's just the resultant. They are not worried about the resultant, so which means there's no even need for us to represent this on a diagram. In order for us to have, we just need the formula. Remember, the formula for calculating the resultant is the square root of the horizontal component squared plus the square of the vertical component squared, like that. So that is what we have in this case. So the horizontal, you just take this. So even you can neglect that negative, it's not important, or you can write it, it's not gonna affect, because if you square a negative, it will be a positive. And also make sure that everything is under the square root. Okay, plus you take also this 103,906, everything under the, so this is your hx. From your formula, your hx, you obtain this value, so this is the one that you square. Your vertical vy here, so that is what you have from your formula, and this is going to give you 238,814 to 81416. So this will be 814, and it will change. It cannot change, so it will just remain as 814 because there is 16 and so forth in Newton, like that. So that's our resultant. So as you can see, we are not even asked about the direction and so forth. We just need the resultant, that is the resultant only, that is going to keep this system in equilibrium. So we are not worried about much in this case. So that's it, guys. Let's see another part of the question, which is on 3.4. Now they're asking us to use the rough truss that you're given, the one that we just drawn and so forth, and they are now saying determine the magnitude of the forces AE. So we've got this AE here, and ED, E to D, and C to G, this one C to G. All right, so let's see, guys, what we can actually do in this case. Okay, so remember, let's say we are working with AE. We are going to take this upward force here on AE. We are going to work with upward forces. So I'm just going to put it this way. This is 3.4. All right. So for AE, I'm going to take these upward forces, just this branch only, 45, and this branch only. I'm not going to take everything, just like this. You understand what I'm trying to say? This is my A, and this is my E, and I am having 45 kilonewton here. All right, and there's an angle of 60 degrees in between here. All right, so for the meantime, I'm not working with D, so there's nothing that I can put there. So working with this AE, guys, as you can see, we are having an upward force. So we know that if we are to relate to say upward forces are equal to downward forces, the sum of these, using the vertical components. Okay, remember, whenever you work about upward forces, you are working with what? Vertical components. So if I'm to use vertical component, I'm going to take this F up, which is 45, which is equal to the vertical component here, which is on top, it's above the line, so it's a positive, so it's AE sine, so it's going to be AE sine 60 degrees. Remember your vertical component, guys. Okay, so in order for you to have AE, going to divide by sine 60 degrees by sine 60 degrees. All right, so this is what you're going to have. So your AE is going to be 45 over sine 60. All right, so if we divide 45 and sine 60, we are going to obtain something like 51,9615 2, something like that. So it's going to be 51,962. That's what you're going to have, guys. And these are newtons, kilonewtons. All right, so this is going to be kilonewton. So these are kilonewtons, guys. And as we talked about previously, that AE in this case is a strut. Remember from that diagram that we drew previously, that one is a strut. So if I am to calculate E and D now, as you can see where D is, it's on the horizontal. So I'm going to work with the horizontal components. Okay, so I'm going to take it this way. I'm not going, because this one is a straight vertical, so there is no way it can play a role on the horizontal component. There's nothing that it can use, so I'm going to just ignore it. Okay, I'm just going to ignore it because now I'm working with the horizontal components. So this is my A, this is my also D. I neglected D because there's nothing that is going to work out from that because it's on the straight horizontal. All right, so this was a straight vertical, so there's nothing that I'm going to work from this because I'm working with the horizontal components. And just like what we did on that previous question here, when we were working with the vertical, we never took this because it's a straight horizontal line, so you can't use it to work with the vertical. So it's the same thing, we can't use a vertical to work with the horizontal. So that's it, guys. So using these horizontal components, we know that the forces that is to the right is equivalent to the force that is equivalent to the left. So on the right side, what we have, this is where we have got our ED. This D is going to represent a straight horizontal, so that will be ED now. All right, so this is ED. Sorry guys, it's because of this thing now. So it's gonna be ED is equivalent to, on the left side now, we are now left with this AE, but there's an angle that is in between, so it's gonna be AE cos, remember horizontal uses cos, so it's going to be cos 60 degrees. Okay, now it can make sense. So our AE, we have got our AE here, which is 51,962 times cos 60 degrees. So it's just a matter of subtraction because you want to calculate ED here, and AE you calculated before, so you can just substitute, guys. All right, so if we multiply these two, we are going to obtain 25,981. Yeah, that's something like that, which is this one. It's a time. All right, so that's what we have, guys, on ED. So actually on the other part, I wonder why even they ask about this, because it's just a repetition to calculate CG. It's just a repetition of what we did on AE, but just we're working with what, with this side. Are you seeing that? It's just a repetition because we are going to work with CG, which means we're going to work with the vertical because this one is part of the vertical from C. Okay, so it's just a repetition, guys, which means our diagram is just going to be like this. You are taking from the right side now, which means we've got something like this, where we've got 55 kilonewton here. Okay, and there's an angle of 60 degrees here, and as we can see, this is your C and this is your G. So definitely, in order for me to find this CG, I'm going to work with the vertical components because I'm now having F up. So F up, we talked about this, so 55 is going to be, this is still above, so it's going to be CG sine 60 degrees, like that. All right, so this one is just a repetition of the first part, how we calculated AE. So divide by sine 60, both sides by sine 60. Definitely we can have our CG, which is this value divided by sine 60. So we are going to obtain 63,508, yeah, something like that, 5085, which is going to be 509 Newton, and that's what we have. And just like AE, it still possesses the same characteristics, so which means you are still working with S right there. So guys, that's how they ask these questions, guys. You must be very, very careful about these typical questions. So that's it, guys, for number 3 on forces to obtain 15 marks from the first part and so forth. You've got your 15 marks. And question 4, which is on friction, the first part is just to state 4 principles of kinetic energy. Whenever you are working with kinetic energy, what are the things that you are supposed to think of or to note of? Okay, so we've got a lot of them. Kinetic, friction, that is dependent on the nature of the surface in contact, independent of the speed, independent of the size of the area in contact, and proportional to the perpendicular force between the surfaces. So there are so many presentations. So if you have got others, guys, you can just let me know on the comment section so that we can also add them on our next classes, so that it can help others also to learn. Okay, on 4.2 we are given a steel container full of copper strips is pulled downward against an incline. So take note, it is being pulled downward against an incline of 20 degrees by a tractor. The mass of steel of the container is 2,460 kgs. The pulling force of the rope forms an angle of 25 degrees with the incline. Okay, so take note, there is the pulling force in this case is making an angle of 25 degrees with the incline, and the coefficient of friction between the surfaces is 0.46 in this case. So take note, guys, of what is happening. We are having or let me represent with a diagram so that it can be understood in a much better concept. We have got something like this, which is a container of copper, whatever that we have, guys. Take note, guys, the mass of this copper, guys, 2,460. Okay, the lot, a lot. So there's an angle of incline, which is basically before everything that we had an angle of 20 degrees. This is from the incline where we have got our copper here with a mass of 2,460 kgs. All right, then here they are saying a steel container full is being pulled downwards. So which means if it is being pulled, that is where it is going to follow the direction by a pulling force of the rope, which forms an angle of 45 degrees. So if it is pulling downwards, this is down here, guys. This is where we are having our block, and it's going down here. So which means for it to go down, there is going to be like this. For it to be able to go down, there is a force which is pulling this way. So this is where we have got our F. Take note, there are so many ways of presenting this diagram. There's a question which will ask you when it is pushing upwards. When it is pushing, this arrow will be facing this way. Or it can be pulling up. When it is pulling up, this arrow, it is going to be like this if it was pulling up, but this one is pulling down, so it is going to be like this. All right, so this is what is going to happen, and this one that is pulling is having an angle, that is where we are given an angle of 25 degrees. That is from what? From this force, the pulling force, which is the one that we do not know, which is F, is making an angle of 25 degrees. So therefore what is happening? According to this F, definitely there is a component F which is parallel, which is perpendicular, which is going to be, but in this case, yeah, it's opposite to this, so it's going to be F sine 25 degrees, and this one is going to be F cos 25 degrees, the one that is going this way. So definitely the body is going in the same direction because that is where it is being given. So whatever that the body is going to oppose, for this body not to go downwards, is going to be your frictional force. Now whatever that is going to oppose, because the body is going downwards, so whatever that opposes is now your frictional force. And definitely, as we know, this is going to be like this, so that we can have our our weight component here due to the what due to the mass of 2460 kgs. We shall have our gravitational components due to this, which is our F perpendicular, which can be written as FC, okay, where we know that this one is going to be mg cos theta, all right, which is cos 20 degrees, and our F parallel, which can be written as Fs, which we know this one is going to be mg sine theta, and ways like that. All right, so that's what we have. And also we are given the coefficient of friction, which is 0.46. We are given the coefficient of friction, which is 0.46. Now the question is to calculate the tensile force in the rope. What is that tensile force, which is the value of F? So definitely, guys, remember, also we have got our normal reaction here, which is going to be opposed with what? With FC, which is due to the gravity, but is not the only one that we have, because also there's this one which is going up. So we've got 1, 2, 3, which affect each other there. So in order for us to have the value of F, we are going to work out from these guys. So remember, from the coefficient of friction, we have got the frictional force over the normal reaction. So we have to find this frictional force in terms of F, and also the normal reaction also in terms of F, so that we can calculate the value of F. So how can we calculate, or how can we have the value of this frictional force in terms of F? Take now the frictional force, we are working with the horizontal components here, where we are talking about the forces that we have, which is going to the right, will be equal to the sum of the forces which are going to the what? To the left. So in this case, if we are to check, this is the only force that is going to the right, which is your frictional force. So it is going to be equal to the sum of those which are going to the left. And to the left, we have got this F cos 25, which is going this way, and also our parallel component, which is mg sine theta. These ones are going to the left. So we have got F cos 25 degrees plus, also this is going to the left, which is mg sine 25, which is F, let's just write it as Fs, which is our parallel component. I think if we write it like that, it can help us a lot. Okay, so this is where we have our frictional force. So definitely we have to work aside our Fs. All right, so let's just put aside and calculate our Fs. Remember, from this formula that I gave you guys, Fs is equivalent to W sine theta, which is going to give us mg sine theta. So we said it's mg sine theta, which is mass. We are given the mass, which is this mass here, 2460 times the gravitational acceleration times sine theta. This theta is this one, the angle for the incline, which is 20 degrees. So it's going to be sine 20 degrees. Okay, sorry for that. So if we are to simplify this, guys, we are going to obtain 2, that's going to be 8, not 2, but it's going to be 8, 2, 4, 5, and this is going to go and go 8, 5, that's going to be 4, 5, 4, 2, 1, 6, 1, 5, so it's going to be 4, 2, 2, because it's going to be 4, 2, 1, 6, so it will be 4, 2, 2 in Newton. So that's our Fs, so which means the frictional force is going to be F cos 25, and cos 25 degrees gives us 0.96. This one, cos 25, make sure that your calculator is in degrees. It gives you 0.906, 0.906 F, because there is F, this one, so we multiply by F because it's unknown, plus your parallel component here, which is your Fs, which is your parallel component. So it's going to be this value. So you add 8, 2, 4, 5, 4, 2, 2. All right, so this is your frictional force, the one that you are going to use there in terms of F. Remember, we said we want the frictional force and also the normal reaction, so we have to keep this. And where are you going to use it? Okay, let's just keep it aside. So we have this and we have to calculate the normal reaction now in terms of F. So how can we have our normal reaction? Take note, a normal reaction, these are actually vertical components. We are talking of vertical components, these ones, the ones which are going up and the ones which are going down. So we are going to relate to the vertical components, where we know that the sum of the upward forces must be equal to the sum of the downward forces. So that's it, guys. Sum of the upward forces must be equal to the sum of the downward forces. So what is going up? We have got this normal reaction is going up, definitely, plus also this one, guys, take note, it's going up here, it's going up, so it's F sine 25 is going up, F sine 25 degrees is going up, which is equal to the F down, the one that is going downward, which is your horizontal component, which is FC, so which is equivalent to FC in this case. So this is your equation. So definitely let us make our normal reaction to be the subject of the formula. This is what is going to happen here. NR, which is equal to FC minus F sine 25 degrees. Definitely, if I take this, it's going to be a negative. And FC, where is that FC? We have to calculate. Remember our FC, guys. We said it can be obtained here, FC, which is mg cos theta, where this is your theta. So you've got mg cos theta, where our FC is going to be the mass. Is that mass that we had? 2460 times 9,8 times cos theta, which is cos 20 degrees. Take note, you are working with the component here of 20. So if we are to do this, guys, we are going to obtain a decimal, which is 22654,654,109. So this is gonna change, guys, because this is gonna be 1, it's gonna be comma 1097, something like that. So this 7 gonna change this into 10 and rounds off these two ones. So it's gonna be 110 here, Newton, or just 1. So that's our FC. So you're going to substitute here our FC. So the normal reaction is going to be FC, which is 22654,11. You can just write it as 11. Don't worry about this 0 here. Minus F sine 25. So you can actually find the value of sine 25, then you multiply to F, and sine 25, it's 0,423. So this is going to give us 23 times F, which is F. So we have got our normal reaction, guys, in terms of F. The frictional force in terms of F also. So that means with these values, we can work out our magic here from this formula that we had. Remember, the coefficient of friction is 0,46. We have got this coefficient of friction, which is 0,46, and our main aim is to calculate the value of F, which is the unknown value. So definitely we have to substitute our frictional force, which is in terms of what? In terms of F, this one here, in terms of F. So you substitute 0,906 F plus 8245,422. All right, you substitute over the normal reaction. So the normal reaction, we have this, guys, this is the one that we have down here. That's our normal reaction. So you have to substitute this as it is, which is 22654,11 minus 0,423F. So guys, this part here is not like you are going to have it like this always, that this one is going to be minus, this is going to be plus. No, it changes, it depends with the diagram. Like I said, there are so many diagrams, so the way the diagram is the one that is going to give you the signs on how you work the upward forces and the downward forces, and also about the forces to the right and the forces to the left. So it's not about this to say it's gonna remain like this. No, it changes according to what you are given. Anyways, we want to calculate the value of unknown. Okay, let me have our question. Remember, the question is still to calculate the tensor force, which is F, which is the unknown. f, so it's the one that we need to calculate. So definitely we can cross multiply. So it's 0.46 this value here. So take sure and multiply properly this value and this value here is going to give us 10420,891. Okay, remember it's multiply everything, so we multiply this and this, we are done. We move on to 0.46 times minus 0.43f, so it's going to be minus 0.195f. You round off, it's going to be 91f. Okay, so we are done. This one and this one, this f, which is equal to 1 cross multiplies this side, so 1 multiplies this everything. So as you can see, anything times 1 remains as it is, so this is going to remain as 0.906f plus 8245,422. okay, so that's our equation there. So with this equation, definitely we have to play around our gymnastics here so that we can actually have the value of f, which is the unknown value, transpose this so that it can be a negative. We've got 10420,891 minus 8245. So there, guys, I'm just showing you what you're supposed to do on your calculator, not to say that you're supposed to write this stage. This stage is not even necessary. You can just do it on your calculator, okay, which is equal to 0.906f. all right, here minus, it's going to be plus because it was a minus, so it's going to be a plus here, so it will be plus 0.195f. all right, so subtract these two, that's going to be 2175,469 if we do this properly, and if we add this, we're gonna obtain 1,101f. So how can we calculate f? Definitely we have to divide by this number that is affecting f, which is multiplying. So it's multiplying, you divide by it, but you divide both sides. So if we divide both sides, therefore our f is going to be 19, and this one is a big decimal, 197,902,816. so it will be 903. I don't know what you obtained from a calculator because this was 902,816 and so forth. So if you round off, guys, it's going to be a 2. So this is how you play around these magics, guys, if you're in exam, and you just need to go there with a lot of energy and strength so that you won't miss out this type of a question, because if you are not well energized, guys, you actually miss this question because it requires you to know what you are doing when what to use at that moment. Anyways, that's what we have, and the other question is to list 3 advantages of friction. Yes, we have got, despite the disadvantages that we talk about friction, it has got some advantages actually, which are very, very important in engineering that we need to use, which is enabling of motor cars to brake, enabling of racing cars to corner at high speeds, transfer of power, and just to enable a car to move. All that we actually need it. So it's not all about the disadvantages, the cause of noise, the cause of materials to blunt and so forth. No, there are also some advantages which are there, and which are very, very important anyways, like the ones that we had. Anyways, we have got the question now, which is on question 5. So definitely there we took everything 11 marks. Sorry for this, guys, I just hit this, guys, I'm sorry for this. We are now in hit where we are given on 5.1 a heat treatment process is applied to a 3000 gram steel hammer. So the temperature of the hammer is 180 degrees Celsius and is placed in this, guys, this is a big value, 7,605,500,000 there. That's going to be 6,500 milligrams. Okay, 6,500 from 7 million, guys. This is a lot. And let's just work out here, guys, our information in a better way so that it can be understood. Maybe we list out our information. We've got 2 things that we have remember when we talk about the loss of heat and the gain of heat, these things, guys, you just need to know them. So we've got a steel hammer, and also this one, is it oil? Okay, this one is oil, it's not water. I'm used to water. Okay, so we've got oil in this case. So we've got the heat treatment. The mass of the steel is 3,000 grams, and you know that in a kg you've got 1,000 grams, so definitely divide by 1,000, you're going to have 3 kgs. So we've got a mass of 3 kgs. This is the mass of steel. Okay, then we move on to the temperature of steel, which is 108. So this is the temperature of steel, the mass of steel, the temperature of steel, which is 180 degrees Celsius. It is placed in this value, which is milligrams oil bath. This is oil bath, guys. So which means we've got the mass of oil bath. Take note, this is milligrams. Okay, milli means to the exponent of -6. That is what milli means. So it means we have got something like this. Let me just write it here: 7006 500, like this, times 10 to the exponent of -6 grams. That is what it means. Milli means to the exponent. Hey, -3, guys, and I'm so bold to say -6. This is milli -3. Micro is the one which is -6. This is milli to the exponent of -3. Very sorry for that. And we said to convert to kgs, if we convert grams, we multiply by 1,000. So this is now in grams, so you multiply by 1,000 your answer now. So whatever that you get, you divide by 1,000. Remember, guys, we want to convert to kgs, not grams. So whatever that you obtain here, you divide again by 1,000. So that is where you're going to end up, multiplying by 10 to the exponent of -6. Or you can just put it this way, guys, to say milli is to the exponent of -3, then divide by 1,000. This is going to give you 7, so the mass of oil is going to be 7,0065. This is what you're going to obtain when you do this in kgs. So this is your mass of oil, and the temperature of that oil bath was at 50 degrees Celsius. So this is the temperature that is affecting the oil, which is at 50 degrees Celsius. So the question now is to calculate the final temperature of the steel and the oil, which is the temperature that is going to affect the mixture of these two, the steel and the oil. But we have got a lot of things that we need to know. For this steel that we have, what is the specific heat capacity of that steel? So we have to come here. The specific heat capacity of steel from our information, it's 500 joules per kg. So this is for steel, which is 500 joules per kg degrees Celsius. And we've got the specific heat capacity of oil. This is oil bath, which is 2,000. So this one is going to be 2,000 joules per kg again. All right, so that's what we have there, guys. And using this information, we can actually play around. Remember, guys, I always talk about this formula about the heat, because now it's just 5.1, the heat that is lost, which is equivalent to the heat that is being gained. So what lost here is definitely steel, because take note, guys, our temperature and the temperature of water, the water is gaining. So this one gained, this one lost. So remember, the heat is mass times the specific heat capacity times the change in temperature. So this is the mass of steel, specific heat capacity of steel, and the change in temperature now is going to be temperature of steel minus the final temperature, because it has lost. While in this case, the oil which gained, we are going to have the mass of that oil, the specific heat capacity of that oil, and the change in temperature, which is going to be T2 minus the temperature of oil, which is the initial temperature of oil. So take note about what you have. So let's substitute, guys. Mass of steel, just substitute here, since we want to calculate T2. So we've got the mass of steel, which is 3 times the specific heat capacity, which is 500 times the bracket TS minus T2. So TS, that is for steel, which is 180 degrees Celsius, minus T2, which is equivalent to the mass of oil. That's your mass of oil in this case, which is 7,0065 by the specific heat capacity of oil, which is 2000, times the change in temperature now, which is that T2 that we want to calculate, minus T oil, the temperature for oil, which is 50 degrees Celsius, like that. So working with this is now applying your mathematical skills, guys, to calculate T2 expansion of. There are so many ways that you could use, and so I'm just going to maintain like the method that I explained before, but there are so many ways you can divide these values. All what matters is for us to find the same value of T. Anyway, so let's multiply this and this. We're going to obtain 1500 into 180 minus T2. You multiply these two, you're going to obtain something like 14013 into T2 minus 50, like that. So we have to expand brackets so that we can work out our T2. So 1500 times 180, which is going to give us 270,000, minus 1500 times 2, which is 1500 T2. We multiply this together, 14013 T2 minus this and this here, which is going to give us 70,000 or 700,050. This is 700,050, like that. All right, so transpose our terms, guys. Definitely, as you can see, this is going to come to this side and it's a negative, this one. So once it comes, this is going to be a positive, so you add these two. It's a positive, so you add, which is going to give you 970,650, which is equal to, if I transpose this negative 1500 to this side, guys, it's a negative, so it is going to add, so it's going to be 14013 T2, like this, plus I add this 1500 T2. So if I add these two, I'm going to obtain 15513 T2. All right, so that's it, guys. To find T2, definitely you have to divide by 15,513, 15,513 both sides. Take note, you divide by the number that is affecting T2, not this one. This one that is multiplying T2 is the one that you divide with. So therefore our T2, if we divide these two, we are going to obtain 62,57010 and so forth. So normally temperature, guys, we can use 1 decimal place, but because of their degree of accuracy, we can just maybe round off to 3 decimal places, which is going to be 5070. This one cannot change, which is a degree Celsius, but to 1 decimal place is going to be 62,6 degrees Celsius. So that's it, guys. That's it. How you calculate the temperature, because they can ask you that type of equation to actually calculate that temperature, and you'll be like, which formula to use? Okay, you know the formula, but what to do on that formula? Do we understand what are we doing on that formula? It's very, very important that you understand that. Okay, anyways, let's see the other part, which is on 5.2. we are given now a volume of 0.25. so therefore there we have to take the information properly, guys. Let's just take our information properly. In this case, we've got a volume. This is 5.2 of 0.240 cubic meters of water. So we are working with water in this case, is heated from. So volume, guys, which means we can obtain mass, because once we talk of heating, okay, we're gonna take mass here. Okay, so what's the relationship between this volume and mass? Remember, if you're talking of a cubic meter, it gives us 1 kiloliter, which is 1000 liters, and this is 0.240 cubic meters. So into we're not converting to kgs. We want to convert to kgs. All right, so it's 1000 liters, and we know that for water 1 liter is equivalent to 1 kg also. It's the same, 1 liter 1 kg. So if this is equivalent to 1000 liters, therefore it is equivalent to 1000 kgs. This is for what? For water. These are general. If it is oil or anything, they will give you the unit of measurement, but for water you use 1000. So it's definitely multiplying by 1000, which is going to be in kgs now, so which is going to give us 240 kgs. So we've got a mass here of 240 kg. Sorry for that. All right, so that is our mass in this case, which is the mass of water, and we are given the temperature where it is heated from to. So this is your initial, your final. So you've got your T1, which is your initial temperature, 300 degrees Celsius, our final, which is 540 degrees Celsius here. What else do we have? By burning coal. So this volume was heated by burning coal, so which means we've got also coal here. Okay, let's just write it aside, because remember, whenever definitely you work of coal, you have to think something about its heat value, and that heat value is actually given from your information sheet. Let's just take this, the heat value of coal, which is 30 megajoules, because we might need somewhere where this value is needed, and we do not know about this that is going to be needed, and we'll be stranded to say how or which formula. But if you list down your information, like, it's easier for you to pick the formula because the information is there. All right, anyways, the first question is just to calculate the change in temperature, guys. The change in temperature, simply T2 minus T1, which is on 5.3, 5.2, not 5.3, so this is 5.21. So the change in temperature is simply T2 minus T1. So T2 minus T1, 540 minus 300. These are in degrees Celsius, so we're going to obtain our answer as 240 degrees Celsius. All right, that's it, guys. We move on to 5.2. Let's see the question, what we are given. So on 5.22, we're now given to calculate the quantity of heat that is required. The amount, the quantity, not the amount, the quantity of heat that is, which means you're talking of what? Energy. And energy, guys, that is a Q. We can write this as Q, we can write this as E. I don't know which one you want to use, but it's mass times the specific heat capacity times the change in temperature, and this is required to heat water. So which means we're going to work with the mass of water, the specific heat capacity of water. So we need the specific heat capacity here of water. Okay, so we need the specific heat capacity of water. So from our information sheet, do we need the specific heat capacity, guys, or we need, all right, which is here, it's there. All right, I'm taking this here, which is 4187. So this thing of working a lot of time, guys, you see now I'm now like where to find this value, and the value is clearly given. All right, so that's it, guys. We just have to multiply. Everything is now there. The mass of water, remember we've got the mass of water, which is 240 kgs here, so it's going to be 240 times the specific heat capacity of water, which is 4187 times the change in temperature. So actually the change in temperature is T2 minus T1. So actually we calculated this before, so you can just substitute. Yes, we can write it, but yeah, guys, you can just substitute there. So if we do so, we are going to obtain this big value, which is 241171200, and this is energy, which is measured in joules, so you can even convert to megajoules. So megajoules megajoules like this means times 10 to the exponent of 6. So to convert to megajoules, you divide by you do the opposite. Mega means times 10 to the exponent of 6. So you do the opposite, which means you divide this by 10 to the exponent of 6, or you divide this number by 1 million. That will be in megajoules. Okay, so this is going to give you 241,1712 and so forth. So it's going to be 1 in megajoules. So like I said, guys, I said divide by 1 times 10 to the exponent of 6. It will be in what? It will be in megajoules. All right, so that's your energy or QQ, whatever that you're going to use it, but that is all about heat. That is it. So on 5.23 we now need the quantity of coal required, the quantity of coal that is being required. So take note, this was the quantity of heat, so that is where to calculate heat. But now this is the quantity of coal, which is the mass, like the volume that is going to be occupied, the mass. So we're going to calculate the mass there. That's what we have. So that's it, guys. So anyways, let's just save this. So where can we have this? Remember, guys, I talked about the heat value, and I said this one we must have it because we don't know, we might need to use this heat value of what? Of coal. So we can play around this value because we know that there is a great relationship between the energy, because remember it is the coal that is going to heat, so which means the heat is going to be the same. There is no efficiency here, so the heat energy is going to be the same. So remember that heat energy is equivalent to mass times the heat value, and we need the amount, which is the quantity, so we divide by the heat value by the heat value on both sides. So which means our mass of coal is going to be the E, which is the one that we obtained here. Remember, we've got our E here, which you said E or Q, which is this one. So we're going to take this in megajoules. So this is 241,171, which is measured in megajoules, over the heat value for coal. And we obtained this from our information sheet. We said it's 30 megajoules per kg. This is measured per kg, so you've got 30 megajoules per kg. So definitely, as you can see, this will cancel and our answer is going to be in kgs because it's 1 divided by per kg, so it's gonna be kg there. So we are going to obtain 8, that's something like this, 8,039033. So 9033 cannot be changed, so it's gonna be 9 like that, which is measured in kgs. So guys, this is it in kgs like that. We have got, yes, we can, because this is cold, guys, cold. We need the mass there. How many kgs of coal do we have? What we can do maybe is to have its volume, to say like how many cubic meters, but we can just have this like what we're given, because you're not given to write the units where to convert this to. State 3 advantages of steam. What are the advantages of steam? Remember, if you're working with the steam, you also talk about the steam plant, which means you're also working with what is on the steam plant. So that is why you end up some of these advantages, including the use of coal and so forth, because they work hand in hand. So steel can be used repeatedly, so there are so many ways that we can use there on the advantages of steam. And on 5.4 we now have a question, which is to state the advantages now of the disadvantages of steam. Yes, we talked about the advantages, but what about the disadvantages now? What can we have? What is it that is going to happen? Talking about the layout, we must have it where water and coal is available, readily available actually. Then water can be lost due to evaporation. Then the initial cost about the installation, that steam water is actually very expensive, and due to the combustion that is going to happen, and this is going to contaminate the atmosphere. So at the end, that's what we have, the disadvantages. So but we have what we refer as advantages, and what we need, and but with that what we need, there are also things that we are not expecting to have, but they keep on occurring on that process. So these are one that we are now referring to as the disadvantages now. Okay, so that's it guys on question 5, which is actually on it. So as you can see, that's what we needed guys to actually take 15 marks on this question. So we shall move on to question 6 now, which is on hydraulics. So on hydraulics, there we are given the first part on 6.1 to name 2 elementary experiments dealing with the pressure in liquids. So if you are working with the pressure in liquids, there are so many things that we can have. Just pick any 2 of your choice. So you've got experiment that we can use to show that pressure in the liquid is directly proportional to the depth, the upward and downward pressure at a point in a liquid, to show the relationship between directional pressure in a liquid, and also we can be even to show that pressure in a liquid is independent of the shape and size of the container. So guys, you must have these ones written in a proper way. Anyways, let's move on to the other question, which is so and tempo. So we are given 3 students here who are engineers working on a single hydraulic pump, and recorded the following information: the force on the ram, the force on the plunger. So we just have 2 things here guys, the force on the plunger, the force of the ram. And then the question is to ask, what is the ratio now of the diameters of the plunger of the hydraulic pump? What are the ratio of the diameters? We only have the force on the ram and the force on the plunger guys. Okay, let's just put this as our F on the ram and this F on the plunger, or you can put this as W on the ram, no matter which one is best for you. Okay, there is a great relationship that we know about these 2 actually, depending with how you're going to take it, but we know that on the ram, F over D squared is equal to F over D squared on the plunger. So this is actually our plunger here, and this is our ram. So in order for us to have the ratio of the diameters, we can just create that, make it this to be the subject. I don't know, you're going to write in terms of this D in terms of this one, or this one in terms of this one. It just depends with how you want to write it. So cross multiply FD squared is equivalent to FD squared. So how can we have this guys? We can actually divide by D squared on both sides, and also like this, divide by D squared by D squared. So this is gonna cancel, but as we divide here, we are going to be left with F. So how can we remove this F? Definitely we have to divide by this F like this. So it's gonna be F over F, which is equal to D squared over D squared like this. And we have got D and D, but there's something that is bothering the square, so remove that by introducing the square root. So definitely the moment we introduce square root, we are simply taking off the squares. So D over D is equal to the square root of F over F. So that's what we have, but this is not what they asked us to do. This is just like you've made a formula guys, so just substitute on your formula to say, okay, if I'm having D over D like this, which is the square root of F over F, so definitely let me just substitute the F on the ram divided by the F on the what, on the plunger. So in this case, what is that force on the ram and the force on the plunger? The force on the ram we are given as 580, on the plunger is 125. So it's 580 over 125. So it's going to be 580 over 125. That's F over F. And this is going to give us a decimal, which is 2,1510 like that, which is going to be 151. So if this is D over this, we can even write it as like D over D like this. So you can write it as maybe S to 1 if you want, but it's a fraction, so you can write it as over 1 like this, D over D like this. You can write it as 2,151 over 1 like this. All right, if you want to write it like this, d s2 d like this, therefore you can write it as 2 comma 151 s2 1. So that's a ratio, or just like this to leave it like that. It's still one and the same thing. Then now, what is the diameter of the ram? If the plunger diameter is 0.45, then what is going to be the diameter on the ram? If on the plunger we put 0.45 on the plunger. So it's simply a matter of working with this formula, because we said d over d on 6.2, we said d over d is equivalent to 2.151 over 1, like that. So if this is the case, therefore let's substitute what we are given. We are given the diameter on the what? On the plunger, which means we are given small d. So small d is the one that we have. So cross multiplying here, it shows that 1 times d is equal to 2.15. What's this 2.15, guys? Okay, it's 2.151. All right, this one and this one d. All right, so which means our d is going to be 2.151 times the d, which is this one on the plunger of 0.45. Yes, you can write it in meters, but this is a ratio, does not affect anything, just a number times a number, which means you can obtain your answer in centimeters, just like that, which is gonna be in 0.96, something like that, 0.96795, which is gonna be 8 in centimeters. So like I said, you can put this in centimeters. If you want to meters, then you have to divide 0.968 divided by 100, which is gonna give us 0.00968 in meters. That is if you want to write it in meters, something like that. Okay, so let's see the other question, which is to make a neat labeled sketch to illustrate the application of the Pascal's law and briefly explain its application. Okay guys, this is just an application of the Pascal's, guys. As we know that most of us guys, we are used to this. We've got our plunger, and also now it's because of how I have written it, or I've put it. Okay, anyways, it's still fine. Let me just put it bigger this way. Right, so we've got something like this, f d f here, and this will be our d. So remember, this will be like distributed evenly and so forth. So this is gonna be pushed up, so it's gonna go up like that. So that's it, guys, our plunger and our ram. So that's it, guys, that's what we have in this case. Just a simple diagram, guys. Don't think much, okay? And briefly explain the application. So what is the application of Pascal, guys? Pascal, remember, is all about the pressure that is to be distributed. It must be distributed evenly throughout the surfaces that we are given. So that's what we have. So the plunger piston is used to apply the force of liquid on the ram, pushed upward by the pressure of the fluid, which is going to be evenly distributed throughout. So that's what you have in this case. All right, so let's see the other part now on question 7, which is actually on electricity, there to explain the Faraday's second law of electrolysis. So let's see what we have there. So remember Faraday's laws from the first law, the second law, that law. So you have to know all these laws. So that's what we're having, that is stated that the mass of the substance released or deposited during electrolysis is proportional to the chemical equivalent of the element. So like I said, we must know from the first up to the last one, which is the third one, define electrolysis. Then if you are able to define Faraday's, which means definitely you must be able to define electrolysis, guys, because that's where it started from. So electrolysis is definitely the chemical separation of substance in an electrolyte by means of electrical current. So you're using the current which is part of current that is actually most important in engineering. We need this part, or the use of electrolysis is very, very important, that we understand just the basics of these. Okay, then also the basic of circuits. We are given a circuit, and also just some basics of energy, how to calculate the kilowatt hour. And so this is what you have on electricity, so just like that. So on number 7.3, you are now given 3 cells, each with an EMF of 3 volts and internal resistance of 0. Per cell are connected in series. So which means we have got 3 here of 3 volts, because each is having 3 volts. So if you multiply by 3, definitely we are going to obtain 9 volts. So which means here we've got 9 volts and an internal resistance of, because they each is having 0.4 ohms per cell, so multiply by 3, which is going to give us 1.2 ohm. So we've got 1.2 ohm. That's our RT for the internal resistances. Okay, so the first question on 7.31 is to calculate the total resistance of the circuit. So as we can cross check on our circuit, guys, we have the total internal resistance, we have got the parallel circuit, we have got this resistance on the ammeter, we've got the resistance across A and B. So you have to add everything. So that's 7.31. So our RT is going to be we are going to start with this internal resistor. Just take whatever that you take, plus the parallel circuit. So make sure that everything is into consideration. We've got the parallel component, we've got our R4, which is this one through the ammeter. We have got R3, so we add everything which is across the voltmeter there. So which means that's what we have in this case. So as we can see, we have to substitute which is our RT, the total internal resistance of 1.2, plus the parallel. Whenever you're working with a parallel, remember I told you guys it's all about the product over the sum. As long you're working with the 2 resistors, just multiply product of the 2 resistors over the sum of the 2 resistors. So it's 2 by 3 over 2 plus 3. All right, then we move on to R4, which is 0.4, plus R3, which is in this case between A and B, which is these 2 ohms, like that. All right, so that's it, guys. You combine everything there. You have to combine everything. So our RT in this case is going to be 1.2 plus product over sum here. Yeah, it's going to give us 2. So this is 2 plus 0.4 plus 2. So if we add everything, we are going to obtain 4.8 ohms. So that's our RT, which is the total resistance of the circuit. Then on 7.32, what is the ammeter reading? So this is our ammeter here. So in order for us to have the ammeter reading, we are talking about the current that is flowing into the circuit, because the current, the total current, is the one that is going to flow through the ammeter. So you are simply calculating the total current in this case, where we know that the total current in this case is equivalent to the total voltage over the total resistance, of which the total voltage, we talked about this, we say we've got 3 times 3, where we obtained 9 volts. So we are going to use 9 divided by 4.8, the one that we just determined. Now remember, we just obtained our internal resistance here of 4.8, so we have to divide, and this is going to give us 1.875 amps. All right, so this is our total current, which is the current that is flowing through the through the ammeter. Then the voltage across AB. So where is our AB? This is our AB here. So definitely the voltage across AB is going to be equivalent to the total current, that is the current that is flowing, times the resistance across AB. So that's the total current times the resistance across AB, which is the total current is the one that is flowing through the ammeter, which is this one of 1.875 times the resistance across AB, which is our R3 in this case, which is 2 ohms. So remember, that's it, guys, and that will give us 3,75 volts, because we know that voltage is current times what? Times resistance. So the current is the total current. And what about the current that is going to flow through the 3 ohm resistor? Which one is that 3 ohm resistor? So we have to locate where we have the 3 ohm resistor, and the 3 ohm resistor is on the parallel circuit. That is where we have the 3 ohm resistor, and we want the current that is going to flow here. And the only thing that we know in a parallel circuit is that the voltage is the same in a parallel circuit. So if the voltage is the same in a parallel circuit, therefore let us first calculate that voltage, because it's easier for us to have it, because we simply need to have the total current times the total resistance of the parallel circuit, which is the total current. We calculated it, that is for this ammeter, which gave us 1,875. So it's 1,875 times the total resistance of the parallel circuit, and this was the parallel circuit here, and we used product over sum here, and it gave us 2 here. So which means we calculated this and obtained 2. So we multiply by 2, and this will give us something like 3, and we're having the same value like this one, guys. Actually, we're having the same value. All right, we are having the same value in this case. All right, so the other parallel in this case is the one, guys, that I want us to work on here. Okay, guys, this was actually 1,2, not 2, but 1,2. So I hope someone even here, it must be 1,2 plus 1,2 plus 0,4 plus 2. Yeah, now it can make sense. So this was 1,2. I hope it didn't affect the other question though. All right, so this will give us, if we multiply properly, therefore we are going to obtain 2,25, because like I was surprised, like, to say, where is this 2 coming from? Okay, this is 1,2 there. So we've got the voltage in the parallel circuit now from the other parallel. Please, guys, I want you to correct this one, okay? From this, please correct. This is 1,2, so that it will give you 4,8. I just want you to correct that. So it's being tired, guys. It's a full paper, remember. Anyways, so what is the current now, so that we can have our 4 marks through this 3 ohm? We have the voltage, and we said in a parallel circuit the voltage is the same. So if the voltage is the same, therefore the current in 3 ohm resistor is going to be 2,25, which is the voltage for the parallel circuit, over the 3 ohm resistor. So you divide by 3. So 2,25 divided by 3, which is going to give us 0,75 amps. So that is the current that we are going to have in the 3 ohm resistor, and this is to give us 14 marks on electricity, guys. So as you can see, guys, these are actually the typical marks that the question papers here for electricity: 14 marks, 11 marks, 15 marks, something like that. So guys, you have to revise a lot. Okay, anyways, on question number 8, which is on chemistry, normally chemistry, guys, is just to know these definitions, and it's nothing much, and there's only about 6 marks, 7 marks, and so forth. That's chemistry. So the first part on chemistry there was to list the properties of ion, of an atom. Okay, so what are these properties of an atom, guys? Okay, let me just list the one that I'm having. In fact, there are a lot of these properties, guys, a lot of. So you can just list the ones that you think is the best. All right, also we have got this, also a continuation. So these properties, guys, an atom, remember, guys, it's even they can ask you to have a diagram of an atom where you've got the nucleus, which contains of what, the neutrons and the protons. Where actually neutrons, these are uncharged. If they are neutral, there's no charge, and the protons, which are positive. Then outside now, that is where we are now having our electrons and so forth. So these are the properties now that they want you to just know about them in an atom. So that's it, guys. And to name 3 elements of a compound limestone. So a limestone, we can name it as an element, we can call it a stone or what, but this limestone has got a consists of calcium, carbon, and also we've got oxygen there. So that these are the elements, or what can be combined to give us that limestone. So that's what we have. So that's it, guys, from this question paper that we had from the 2021 July August exams. So that's what we had, and this 6 marks for this, and to make a total of 100. So that's it, guys, from maths on African motifs, working on engineering science N3 and N2 and 4 and so on. So not to miss these classes, make sure that you are part of the family maths on African motifs. We're subscribing to the channel, and also turning on your notifications so that you'll be part of the notifications which are going to come in further. But that's it, guys, and also we just say let there be light.